Baby, I just sit and look pretty. Period.
Hi everyone. So today we will continue the previous lecture, which is a part two of the lecture series on the atmospheric and oceanic circulations. And before I start my lecture today, I would like to remind you all that the first exam will be on next week on Wednesday, and I'll be posting. Please make sure to check your iCollege. I'll be posting announcements, and then also I'll in the announcement I'll describe what you need to prepare for the first exam. So all the materials you need, and including textbook chapter summaries. These are chapter summaries of the textbook. So but we also have also included in the syllabus some topics that are not fully covered on the textbook, and so such as the atmospheric and oceanic circulations, and then I'll post reading material, and most importantly I'll post quizzes that are very similar, question and answers. They're not quizzes, but these are question and answers for you to use as a study guide, because they're very similar to the exam in terms of format and also content, right? And again, for some of you who are still interested in purchasing textbook, please reach out to me. And then I think a few students having problems accessing the textbook online, so I'll be happy to provide hard copies of the textbook. But for the exams, I'll try to make all the materials you need accessible. You need to prepare for the exams, and accessible to you all in terms of textbook chapter summaries, or relevant texts uploaded to the on iCollege for you to read, right? So last lecture we were talking about the general atmospheric circulation, right? And then you remember that, like, the most important thing we discussed how the winds are very important, and they control the general atmospheric circulations, right? And we talked about how the gradient is actually very important, because it's the gradient in the pressure. When we're talking about atmospheric circulation, it's the gradient that's important control on the movement of the very important control on and then that allows the winds to blow, for instance, from the high pressure points that are usually located in the mid latitudes to the lowest pressure zone on the equator or near the equator, right? And then you remember that, like we discussed, that the ITCZ, the position of the ITCZ, is not actually permanent, and it moves northward during the northern hemisphere summer, that is in June, July, August, and then moves southward during the northern hemisphere winter season, and the southern hemisphere summer season, that is January, February, March, right? December, January, February. And but when we talk about the global ocean circulation, the gradient, I would like to remind you again. Right, let me put this one here. I would like to remind you again that the gradient is also is equally important, right? So when we talk about the global ocean circulation, we're not only just talking about the surface currents, right? What's happening in the surface, but the most importantly, what's happening in the deeper ocean, So I'll show you in the next slides how that's important in regulating global temperatures, right? So the ocean is actually, we can consider it like an integral part of, and the main driver of, like, the climate system, right? And so we can't really view the atmosphere as if it is an independent body, right? But it's the interaction between the ocean and our oceans and the atmosphere is what drives the climate. So we'll talk about surface currents, how they are important, and how they drive upwelling zones, like as I'll explain in the next slides, and then what actually controls the water movements, like different water masses, like how they what controls the movement of the in the deeper ocean particularly. So the previous lecture talked about cyclones and anticyclones, right? And the fundamental difference between the two. And so we have a more or less similar situation in the ocean as well. Like, for instance, if we look at what a gyre is, it is this circular moving current systems within an ocean basin, right? And so the surface winds are important, and then the rotation of the Earth is also important. So in a way, it's a reflection of like what we have in the atmosphere. So we do have it also in the ocean as well, right? And but for surface currents, these are the currents like in the surface of the ocean. But so as a result, there is a direct interaction with what's happening in the atmosphere, right? That becomes so the surface currents occur when we have at the top of the ocean layer, where they have direct interaction with the atmosphere. So what happens is that the winds we have in the atmosphere, surface winds in particular, they become very important. So what happens is, as the wind blows, of course, it moves a portion, not all of it, right? A portion of the upper layer of the ocean, right? And then that actually ends up like moving the adjacent layers deeper in the ocean. So the surface currents, they trigger a movement of the different layers we have in the ocean, and up to a certain point, right? So the net effect of the surface currents is at the top, 100 meters or so of the ocean as a whole is dragged at almost vertically and to the direction of the wind, right? So, but for you, it's most important to remember that, of course, when we're talking about surface winds, they are driven by, as you may recall from the previous lecture, the Coriolis effect is important, right? And then, of course, when we're talking about the wind, they are fundamentally driven by the pressure gradient, the existing pressure gradient, and then Coriolis effect, and then, of course, as they interact, we're talking about surface interaction, the frictional force becomes relevant as well. Okay, so we know how surface currents move, and then how do ocean currents affect the climate then, right? But it's not the surface. It's not just like the currents we have at the surface that are relevant here, but we have very important movement of different water masses at depths, and those impact the climate in very both simple and complex ways, as I would explain in the next slide, right? So for the atmosphere, I've told you that like the pressure gradient is important, right? Basically, when we're talking about atmospheric circulation, we're pretty much talking about the winds, right? The different types of winds. And then when we're talking about what drives the different types of winds we have is fundamentally they're driven by the pressure gradient, right? While in the ocean, now we have a different variable that actually controls the global circulation of the ocean. So now, instead of wind, of course, the winds are very important. Control the what's happening in at the surface. So like surface or ocean currents, but the deeper circulation, the deeper water circulation and its formation is driven by salinity instead. So salinity, the salt content of the ocean, is very important, right? So because the salinity, what salinity does is it changes it controls the density of a water mass, right? So the gradient in the density for the atmosphere, remember, it's the gradient in the pressure, right? The atmospheric pressure. Now for the ocean, the gradient in the density actually controls what we call the global thermohaline circulation, as I'll show you in the next slide. But I just want to briefly mention one very, very important current in the ocean that's like very important, that controls the weather patterns in the northern hemisphere, right? We talked about, for instance, in the last lecture, about how the jet streams form and how the jet stream is important. But now in the ocean, we also have like what we call the Gulf Stream. So what the Gulf Stream does is that it actually transports warmer water from the Gulf of Mexico and to the Atlantic Ocean, right? So it's basically what the ocean does is, like, the purpose of the ocean is it redistributes energy. It redistributes heat, right? So along the way, it brings warmer water to closer to the continental Europe, right? Depending on the extent, right? The intensity of the Gulf Stream, right? Depending on the strength of the Gulf Stream, then we can accurately we can set our expectations of what the summer would look like in a certain parts of Western Europe, or including also it also impacts the impacts like the weather conditions in Northern America as well, right? So it's a very, very important piece of the global ocean circulation, where we have the movement of heat, right? The transport of heat from the warmest parts of the Earth and all the way to the northern high latitude, right? To including Iceland, right? So the ocean is always trying to regulate global temperatures, right? So it's a very, very, very important element within the climate system, right? Okay, but now let's talk about upwelling, right? So we also have like both, like I said, I'll come to the deeper ocean circulations and what drives them in the next slides, but I just want to briefly mention what upwelling is like. Upwelling simply is the rising of cold and nutrient-rich water and then that transport to the surface, right? And what drives upwelling? Of course, again, we're talking about why surface winds are relevant, right? It is actually the transport of nutrient-rich water, and because of the surface winds, and that brings and more nutrient rich, of course, and also colder waters to the surface, right? So these are what you see here are important upwelling zones, right? And then for upwelling, it's also, now the surface winds are important, but it doesn't mean that all the coasts have upwelling, right? So the topography is important, and so it's now we're talking about surface winds bringing nutrient-rich deeper water to the surface. So we're talking about an interaction between the coasts, as you can see here, and also the surface winds, right? So the surface winds are a very important elements. Important elements in this puzzle, right? So these are the upwelling zones we have. So remember, if it brings concentration of dissolved nutrients to the surface, that means the productivity in the ocean is also significantly increased, right? So you'd expect the fish industry to thrive in these upwelling zones, right? Because now we're talking about nutrient rich waters come into the surface, and then so that translates into high productivity, right? So if you're talking about the coastal areas, many coastal areas in the US, they have strong upwelling zones, of course, and then that means increased productivity, right? And if we look at, for instance, the California coastal upwelling, and you see, for instance, this temperature, what you see here is temperatures, colder waters, right? The colder waters are also rich in nutrients because they are coming from the deeper ocean, the colder waters, and then these are exactly where we have significant upwelling, right? Simply what upwelling is, the movement of the transport of deeper water from the bottom layer of the ocean, and which is also rich in dissolved nutrients to the surface, right? That movement we call upwelling. And then, of course, there are important implications for fish production and for the fish industry, for the fishery industry in general, and where the upwelling source are an important the upwelling zones in terms of the fishery industry, they sustain the livelihood of millions of people residing in these regions. Okay, now back to the global ocean circulation. So now you should view the global ocean circulations both vertically and horizontally, right? So for instance, we have the vertical transport of different ocean masses because of the density differences, right? As I'll explain in the next slide. So the density difference is that gradient needed to drive the ocean circulation, right? So of course, we also have mountains in the ocean floor, right? So we have different water masses if we're looking at the different oceans, right? And then depending on what we have, the topography, right? Topography of the ocean floor, and it also limits or controls the extent of mixing we have in the deeper ocean. But remember, the global thermohaline circulation or the global oceanic circulation is fundamentally driven by density currents. How? I'll explain in this slide. So what are the most important variables? Remember, I said salinity. Now we're talking about salinity changes that's driving the ocean circulation, right? So when we're talking about salinity, there are very important puzzles I would like you to remember. So for instance, sea ice. How does sea ice impact ocean circulation? You may ask. So sea ice impacts the ocean circulation because the water mass below the ice is actually colder, and then also high saline water, right? It actually allows for the formation of deeper water formation, right? As you can see in this figure, so I'm showing you how the global sea surface salinity looks like globally in the global ocean, right? So we have two red patches here, right? One is, expected, right? One is expected. Well, it's the tropics, of course. temperatures are higher, and then it makes sense to expect higher salinity than places, for instance, the tropics. You would expect it, high salinity waters compared to the poles, for instance, here, right? Salinity is much lower. But in North Atlantic, something very important happens, right? So this is the region where, well, it's not the tropics, so the water is actually cold enough, while temperature is colder, surrounding temperature is colder, and then it's also like in the high latitudes, and the water is it has high salinity, right? Because it has high salinity waters, it actually triggers the movement, the vertical movement of those high salinity, dense, cold waters, and the sinking of that water from the surface all the way to the deeper parts of the ocean, and then along the way, it actually what we call it triggers a deep water formation, right? So that very cold and also high saline water and forms in the northern high latitudes, like above the northern Atlantic Ocean. We have a deep water formation, and then because of the density gradient we have across all the oceans, then we have what we call the global ocean conveyor belt, right? So we have this movement of water masses with different densities, different salinities. They actually circulate globally, and then along the way they actually maintain an equilibrium, and then along the way, of course, maintaining the global temperature of the planet, right? Okay, let me go back to density currents again. So now in the previous slide, you see, okay, if you look at salinity, we have like high salinity waters, strangely in the northern Atlantic where it is cold. Of course, you would expect it, the salinity to be a little bit, the water to be a little bit fresher, as you can see here, relatively fresher during when it is cold, but that's not the case because of what we have. The effect of what we call those sea ice, right? But generally, if we look at the evaporation, the evaporation extent in the global ocean, of course, we have the higher evaporation, and that means net precipitation loss in the tropics, right? What you see here in blue is where we have net precipitation loss, so that means the extent of evaporation is very, very high, right? But that's expected. But this change, right? A change in temperature, and both in temperature and precipitation, of course, influence the global thermal circulation. How? Well, of course, if the salinity of the salinity of the water changed, it actually changed the gradient between the different oceans, right? Now, for instance, if the gradient, when we're talking about the atmospheric circulation, if the gradient is weak, right? If the pressure gradient is weak, the winds will also be weaker, right? The winds will also be weakened. So in the same way in the ocean, if the gradient is weaker, then the circulation, the circulation is also significantly weakened, right? And if you ask me how the global ocean circulation is very important, like I said, the oceans are critical because it's a very, very important source sink for carbon dioxide, right? So the oceans we have, they help us in a way naturally mitigating climate change, right? Because they absorb the heat that's consistently being released to the atmosphere, right? So it's a heat sink in a way, right? But up to a point, right? So for instance, the oceans have absorbed about 30 times more heat than the atmosphere, right? So it's actually, if we view the planet, it's basically the oceans and then tiny pieces of land, like, so the ocean, in terms of area, it actually covers like the large portion of the planet. And so it's really a very important thing, right? The ocean is like a very, very important thing. And then also, so in a way, it has always been, it always regulates the heat transport and the try to maintain that equilibrium state, right? And then when we talk about the ocean's role on climate, of course, the ocean circulates slowly and usually on time scales of decades to centuries, right? And of course, it's a major source of heat to some regions like the North Atlantic, but it also sets long-term patterns in atmospheric circulations and affecting climate systems, not only on seasonal, interseasonal basis, but as I will talk in the next lecture, and also impacts like the poles. We have this coupled atmospheric and oceanic circulations, like the El Nino Southern Oscillation and the North Atlantic oscillations, which actually impact the climate on more or less on semi-decadal timescales, right? So like I said, the ocean, it has been absorbing that extra heat that has been consistently being released to the atmosphere. So in a way, the ocean mitigates climate change, but up to a certain point, right? So what I'm showing you here is a very, very important figure. And what you see here in red is the global ocean heat content. So what do you see here? Well, the ocean heat content, right? So it shows you that our oceans are significantly warming, right? Especially the deeper ocean, where I'm talking about if we're looking at the mean changes in heat content for 0 to 2,000 meters of the ocean, then what we see is significant, there is a significant positive trend, right? This has an important implication for climate, right? Because the ocean, of course, it's absorbing absorbing the heat that we are emitting, but we don't want the ocean to be to contribute to the warming. How does that contribute to the warming? Of course, the warmer waters, like if the ocean keeps warming, the efficiency of it, the oceans absorbing the extra carbon dioxide being released to the atmosphere decreases as the ocean warms, right? It's exactly same way as, think of it this way. For instance, if you're drinking a Pepsi, right? You'd like to drink it cold, right? Because if it is cold, that means the cold liquid absorbs. It's better at absorbing and maintaining the carbon dioxide, right? And then when you drink it, like it feels better. But if it is a little bit warmer, then all the carbon dioxide is gone, right? All the carbon dioxide is released, and then in a state of if it's completely different when you drink it warm. So the ocean, while it's a very important regulator, but if it keeps warming, and then it would also be a very, very big, in a state of being a sink, it would be a source for that extra warming, right? So the ocean heat content, of course, changes from the different oceans. They have the amount of energy absorbed by the oceans that we see. Like the climate, of course, some places are warming so much faster, right? And then some places are warming relatively slower compared to others. Then we also see these differences when we're looking at the ocean, right? Okay, so if you ask me how the global warming effect on the thermohaline circulation, right? So when we talked about the global oceanic circulation, or even the atmospheric circulation, I've mentioned this a million times already, right? But we'll mention it again because it's very important. The gradient is actually the gradient between different variables is what drives the weather and the climate system we have, right? For instance, if there is no difference in warming, right? If we don't really have any differences in warming, then you don't really have any differences in pressure either, and then nothing happens basically. So, but for the ocean, again, now we're not talking about pressure differences, right? Now we're talking about density differences. So the gradient, well, the bigger the gradient, then the stronger the convection is, right? The stronger the movement of the different water masses is. So if I ask you, what would happen to thermohaline circulation? Well, it has different names. What we say the thermohaline circulation is the global thermohaline circulation. It's basically the ocean, the global oceanic circulations, also called the Atlantic AMOC, or the Atlantic thermohaline meridional circulation, right? So also the Atlantic conveyor belt. So if the gradient, if the warming it keeps increasing, it can potentially kill the gradient we have, right? The density gradient we have, and then what would happen is that the Atlantic conveyor belt may actually potentially shut down. What would happen? And then we have instance of it shutting down, and in the past, so it has a significant impact on global temperature. But I don't want to spend a lot of time in this figure. But what I want to show you is that we have ways to actually reconstruct the paleoceanographic conditions going back in time, and I have a lecture dedicated to it, but a separate lecture dedicated to paleoclimate and how that is important. But what I would like you to show here is we have an instance of the what we call the AMOC, the global conveyor belt completely shutting down in the past. So what does that mean? Well, for instance, let me take you back to this figure, right? So what drives, again, the global ocean conveyor belt? Oh, of course, the deep water formation. And what does the deep water formation do? Oh, of course, it creates a density gradient, right? So, but instead, what would happen if we pump, right? If we increase the warming, of course, there will be more melting of fresh water from the high latitudes, right? And then that would actually alter the density, the salinity content of the water, right? And then that subsequently triggers a collapse of the gradient, right? What would happen then? So if we don't really have the gradient, then we don't really have the transport, the transport of the different water masses from the tropics to the poles, or the transport of colder water masses to the tropics, where it regulates the tropical temperatures, is actually severed, right? And then if that happens, and then the certain places, because the ocean is a very, very important regulator of global temperatures, and then some places actually would be it would be very difficult to live in certain parts of the world, because we don't really have a significant reduction in the global thermohaline circulation, meaning that some places would be hotter, and then some places will also be very cold. So at the end, really impacts the life in a fundamental way, right? So if you ask me, so could this happen again in the relatively near future? Yes, So global warming causes increase in rainfall in the North Atlantic region. So the surface water becomes fresher and then less dense. And then, of course, so when it becomes less dense, then we have the collapse of the gradient that actually drives the different oceans to connect, right? The transport of the different water masses in the deeper ocean. And with that, that will be the end of today's lecture. And on Monday, I'll talk about a very, very important climate phenomenon that actually connects both the atmosphere and the ocean, that is the El Nino Southern Oscillation. So please wait for the announcements, and then I'll give you all detailed instruction how to prepare for the first exam next week, right? Take care.